Sir.
Okay. Okay. So I will try to share the my screen. And okay. Okay, I've shared a slide. I mean, I don't know whether
it's visible. It's visible.
It's visible. Okay.
Yeah.
Maybe I can make it full screen.
Yeah, you can.
Yeah, I suppose now it's full screen.
Yeah.
Okay. Yeah, it's moving. Let me see if. Okay. Okay, it moves like that. Okay.
We will wait for 5 to 10 minutes, then
Okay.
we'll start.
Okay.
Yeah.
Okay, the audience is mostly, I guess, bachelor student.
Yeah, maximum.
Bachelor students. Okay.
Faculty is also there, but maximum of the students.
Okay.
Sir, we will wait for another 2-3 minutes. As soon
Okay.
as our principal sir will join, we'll start.
Okay.
He's in a meeting just for 4 or 5 minutes. Thanks. Suman, are you there? Suman? Suman?
हाँ जी मैम।
सुमन सर ने ज्वाइन किया कि नहीं अभी तक?
सर ने नहीं मैम, अभी तो सर नहीं आए।
ओके।
मैम सर आ गए हैं।
ओके फाइन। ओके या गुड आफ्टरनून सर। हाँ
good afternoon.
या
Good afternoon, Professor Justin. Oh,
सर कैन वी स्टार्ट?
yeah, please, please.
Yeah,
I'm sorry
thank
for late little bit.
या नहीं, इट्स ओके, थैंक यू। Yes, good afternoon to one and all. Myself, Dr. Ashu Gupta, and it's a moment of great privilege and honor for me to extend a hearty welcome to our keynote speaker, Professor Justin David, to our principal sir, Professor Ravi Narayan Kar, to our IQAC coordinator, Professor Kusha Tiwari, and to all our participants. I feel highly elated to welcome you all at the launch of SLC Eminent Lecture Series 2021-22, and we would like to extend our gratitude to Professor Justin for accepting our invite and to be our first keynote speaker under this series. Thank you, sir. Thank you so much. I'm also grateful to our principal, sir, for always motivating and guiding us to organize such kind of events. Thank you, sir, for all your support and encouragement you have given to us. And basically, the basic purpose to launch these lecture series is to provide a platform for a robust exchange of ideas to strengthen the high levels of intellectual excellence and to motivate our stakeholders to meet the new challenges of real world, to promote the best in class research, and to so on. Actually, there are many more reasons for holding these kind of activities, which are not able to, I can't share on this platform all the. I wish through this initiative we are successful. Just a minute, my computer is getting hang. Sorry. I wish through this initiative we are successful in achieving all our goals, and mainly if we can galvanize research activities in our institute. Now, without taking much time, I would like to give brief introduction of our eminent speaker, Professor Justin, who will be speaking on topic Entanglement Entropy and Holography. Professor Justin obtained his MSc degree in 1994 from the Indian Institute of Technology, Kanpur, and PhD degree in 1999 from Tata Institute of Fundamental Research, Mumbai. He did postdoctoral research work at the University of California at Santa Barbara and International Center for Theoretical Physics, Trieste. He joined Harish Chandra Research Institute, Allahabad, as a reader in 2005, and then moved to the Indian Institute of Science in 2007, where he is now professor and chair of the Center of High Energy Physics. Professor David was a DST Ramanujan Fellow from 2010 to 15 and is the Fellow of Indian Academy of Sciences, Bangalore, and also the Fellow of the National Academy of Sciences, Allahabad. Professor David has made significant contributions to the microscopic understanding of black holes in string theory. His work provides the precise derivation of the Hawking formula for near external black holes, as well as the counting function for the degeneracies of supersymmetric four-dimensional black holes. He has contributed extensively towards holography in two-dimensional conformal field theories. Also, he has obtained correction to entanglement entropy in two-dimensional conformal field theories and identified the universal corrections. And we welcome you again, sir. It's an honor to hear from you. Now, before we can start with our today's talk, I would like to invite our principal, sir, for his welcome remarks. Over to you, sir. Sir?
Yeah.
Yes.
Good afternoon to all of you. First of all, I would like to extend a very warm welcome to Professor Justin. It was kind on his part to readily agree to our proposal of having this lecture. So for that reason, I once again thank him profusely for accepting our invitation. At the outset, as Dr. Ashu Gupta told, that this is a platform we have created for the betterment of not only our students, at the same time also for guiding our faculties, young faculties in working in different colleges of Delhi University also, to look forward to carry on their mettle of research into new frontiers and emerging areas. For that reason, sir, nobody would have fitted better than you. And secondly, also institutions like us who have been basically teaching institutions here, and with the impending implementation of NEP and the larger view of the nation, we also want to integrate. We also want to go vertically, and for that reason also we need some mentors. And for that reason also, none other than Indian Institute of Science would be better fitted than this. So with these preliminary words, I once again congratulate our DBT Shamlal College led by Dr. Ashu Gupta, and IQAC of this college led by Professor Kusha Tiwari, having coming up with the idea of SLC Impact Lecture Series 2021 and 22, for which Professor Justin David is with us. I hope this deliberations will go a long way in shaping or reshaping and thinking and developing new frontiers of research. With these words, once again, I welcome you, sir. And at the same time, also, we have a lot of participants. I also would like to thank them for joining in our maiden venture. Thank you all. Thank you.
Thanks. Yeah. Thank you.
Thank you, sir, for all your support and appreciation. Now I would like to invite our IQAC coordinator, Professor Kusha Tiwari, to say a few words. Over to you, Kusha, Dr. Kusha. Sorry, Professor Kusha. Are you there? Suman, she's there. Suman, Professor Kusha is there?
Maybe she's not there.
Okay.
can
As soon as she
proceed,
will
yeah.
join, she can continue with us.
Yeah.
Sorry. Now, before we start with such much awaited talk, I would like to mention that we will be taking questions and at the end of the webinar. So if you have any question, just text it in the chat box. Secondly, we will be sharing attendance and feedback form in the chat box during the webinar. Now, let us have the pleasure of listening to our distinguished speaker. I invite Professor Justin to deliver his talk. Over to you, sir.
Okay, thank you. Thank you for invitation, and it was very kind of Dr. Ravi to invite me. We met over some occasion for some, and that was the time I just met him a few months ago, and it was very nice that I have this opportunity. I have talked to undergrad and MSc level very less. I mean, we live in ISC, and we talk to a few people. There was very few opportunity for me to talk to people just out of high school and so on, and this is a good platform, and it's a difficult task actually to convey the excitement in these areas, but I will try. I'll try as much, and there might be some words which you might not understand, but you keep them towards the end, and I will try to explain. Okay, so I'll be talking about this topic, entanglement, entropy, and holography, and of course I'll have to explain almost every single word in this eventually. Hopefully, I will be able to convey some aspects of it. It has been something which I've been thinking about for some years with various people and students. So I will try to convey what is it and what is the reason for thinking about it. So let me begin with an introduction. So I just have to say first, it is sort of an important and useful observable to characterize quantum systems. So now, of course, many people might not even understand what's quantum system and so on, but I think some people, people have heard about quantum mechanics, people have heard about solid state and so on. So yeah, I think you can just use that notion. And this quantity, entanglement entropy, is a sort of new thing. People don't usually evaluate. People evaluate very simple observables of simple quantities before. There's a new quantity which has been of recent interest. And I will say why it is sort of interesting to us. There are various reasons why it is interesting, but why it is interesting to us soon. And so before I introduce even this, I have to introduce what is entropy a little bit more formally than what people at bachelor's or MSc level understand it as. And intuitively, I think most of us understand, because the word entropy is also colloquial. And so it quantifies the amount of disorder in the system. And I think people know that just from the definition of the word entropy. But we have to understand it slightly more quantitatively. Now, people who have done an MSc, I think they know this relation. It is defined using this particular relation. Is a small change when the small change in entropy is related to a quantity which are much more familiar, the exchange of heat and temperature. So it's related by this formula, ratio of the exchange of heat towards the temperature at which the exchange took place. And this exchange is sort of reversible. That is the meaning of that even. But this is a definition which you have learned in your MSc or BSc course. But we would need something further than that. We would need to understand entropy a little bit more mathematically and a little bit more microscopically to go ahead. Okay, so we have to understand entanglement entropy and holography, and I'm trying to break it down one by one. So let us go to entropy, and I'm trying to understand, make it a little bit more microscopically and mathematical. So now I think some of you, because I think mathematicians also might be there in this, they know what's the notion of probability. Okay, so like for instance, if you throw a dice, to get one particular face, the probability is 1/6. So That is the notion of a probability distribution. And suppose there is this n outcomes, and associate each probability to each of these outcomes. In the matter of dice, it is just 1 by 6, or in the matter of coin toss, it's just 1 by half. So these are those numbers. Now there's a notion of entropy to a probability distribution. Okay, so probability distribution, of course, satisfies this. If you sum all the outcomes, you get the total number of outcomes. Like if you sum all it's actually 1. Sorry, I made a mistake. It's actually 1 here. So you get 1, and there are various distributions like throwing of the dice or throwing of the toss of coin. Now, what is the notion of entropy to that of a probability distribution? Now, that was actually given by somebody called von Neumann in the 1930s. Okay, so essentially, if you're given this numbers pi, like it's 1 by 6 for a toss of dice, it could be some other set of numbers. You compute this quantity, pi log pi, and you sum over all the possible outcomes. Okay, so this is a well-defined formula. Logarithm, okay, some people might not understand, but I think in mathematics and physics, yeah, I think I can take it that people understand what is log, and you just sum over these things. And that is what von Neumann called entropy. I mean, it's entropy associated with a probability distribution. It's not so familiar. I think people who did physics, this particular formula might not be very familiar. Okay, but okay, so there is this constant, Boltzmann constant, but we will just suppress it right now. We'll talk about pi log pi. Okay, so this is a formula. So given this set of numbers pi, which is a probability distribution, you can compute another number s, which is called the entropy of a probability distribution. And that is it is a simple formula. Now, let's just study some of these properties of entropy, because you might have not seen this, this quantity, this notion of entropy. Let's just study some of the properties. Now, suppose you have a probability distribution in which there are n outcomes, and only one outcome is favorable. That means only one outcome always comes. Like you have a loaded dice, always, the number 6 comes. None of the other numbers come. So that means, say for the number 6, it's 1, which always comes, and the rest is 0. Okay, there's no uncertainty in this distribution, because somehow the dice is modified, and you always get 6. So let's compute the entropy associated with such a probability distribution. Now you have to use this formula, pi log pi. We are suppressing kb just for discussion. There is a minus sign. So there's a minus sign, log 1, because that is pi, 1 log 1, and 0 log 0. Now this you have to understand, because the rest are all zeros, because pi is 0, and 0 times log 0. All this, if you understand this in terms of a limit, I think people in maths know, this goes to 0, in fact. And log 1 is also 0, and therefore the entropy is 0. So if this distribution is always peaked at one particular value, I mean, it's always giving, say for instance, the phase 6, there's no entropy associated, because there's no disorder. You know that you're going to get the, variable 6. Okay, so there's no entropy. But suppose it was a distribution in which all of the events are equally likely. That means it is the usual random dice in which, for instance, 1 by 6 for each of the faces. Okay, so that is this 1 by n is the number of outcomes is 1 by 6. Then if you calculate this, so it's 1 by n log 1 by n. Okay, it's pi log pi, and it's log n. Okay, if you sum it, there are n times of this, there's log n. So thus the entropy here in this case, for when the events are completely random, because anything is possible, then it's just the log of the number of outcomes or number of configurations or the number of degrees of freedom. So this is sort of the notion which Boltzmann had. So Boltzmann had this notion that the entropy is just the log of the number of outcomes or the number of degrees of freedom. And the von Neumann definition reduces to this familiar case in this particular totally random distribution. But the idea of the von Neumann definition is much more general, and we can apply it to much more general situation. All we need is this set of numbers, and then we can just compute the entropy. Now, it is with this definition, actually, entanglement entropy is defined. Okay? So I will just define. So so first, let us go over. Here I have just actually introduced this entropy notion in terms of just a mathematical notion. Given the probability distribution, I can associate a number which is called entropy. Now we want to apply that to a physical system, okay, say quantum mechanics. Now in quantum mechanics, you don't have numbers, you have matrices. If people who have studied quantum mechanics, even in the beginning pages of quantum mechanics, people say, oh, somehow the position has become a matrix, or momentum has become a matrix, or an operator. So people have that notion. So quantum mechanics, somehow, what are the fundamental quantities are not just numbers, they are matrices. Matrices are arrays of numbers. Okay, it's sort of, array of two-dimensional array of numbers. Now, what is a characteristic feature of a matrix? And I think people who study maths, or anybody who did BSc maths, would know that one of the characteristic features of the matrix is something called the eigenvalue of the matrix. Okay, and then that that is a number. That's a number. So therefore, we can define an entropy associated with an n cross n matrix. Say we call that matrix rho. In this following manner: you take the entropy, and the definition is minus. Instead of pi, you just take the eigenvalues lambda I, and take log lambda I. Okay, so pi log pi has been replaced by lambda I log lambda I, where lambda I are the eigenvalues of that matrix. So what I'm trying to do is we are trying to take this notion of entropy to quantum mechanics. Okay. And these are the eigenvalues of the matrix. Now, if you know some matrix algebra, you can, this way of writing the entropy is much more complicated, in the sense that we have to take the matrix, find its eigenvalues, put it in this formula and compute the entropy. But if you know some matrix algebra, we can write the same quantity as a trace. Okay, it's a definition on the matrix. It's an operation on the matrix, and take the matrix rho log rho. So logarithm of a matrix is a complicated quantity, but it is defined. And if people know a little bit of matrix algebra, you know that if the matrix was diagonal, it reduces to this formula. Okay, so that's what I said. If the matrix is diagonal, it reduces that particular formula. Now, this von Neumann's definition can be translated to quantum mechanics by just replacing this pi by the eigenvalues. And in that logic, if you carry that, push that logic a little bit further, you can take that matrix and write trace rho log rho. Trace means an operation which just sums all the diagonal values of the matrix. Okay, so that is a particular way of writing the entropy, von Neumann's entropy, for a matrix. Now, of course, we needed pi, which is probability distributions, to be real and positive. Okay, and that is guaranteed by choosing a particular operator called Hermitian. So this occurs all the time in quantum mechanics. So that is assured, and the positivity also we will see that will be assured by the choice of rho. So it satisfies the input requirements, and given the input requirements, all we have to do is compute this quantity, and that is the entropy. Okay. So I'm actually just though you might not understand all the details, at least schematically, what I have done is basically taken the notion of entropy a little bit more mathematically and translated it to quantum mechanics. Okay. Now, in quantum mechanics, what is this matrix, right? What's the matrix? In classical mechanics, you describe a state of the system by position and momentum. But in quantum mechanics, what do you do? So if you think about some people who have done bachelor's in physics, they will know, at least in the third year, they would know the quantum mechanics is described by something called a state vector, or a wave function psi, which can be described by a state vector, which are basically a set of complex numbers. So it is basically an n valued n objects, n numbers which are complex. And a state of a system is specified by this, giving these n complex numbers. And each sum I is one of the outcomes. Now, how do you construct a matrix from this? and also, okay, you would know this from quantum mechanics that if you sum these coefficients of the wave function, they add up to 1, just like probabilities, they add up to 1. Okay. So how do you construct the matrix from this? So what you do is you write down that set of numbers in this way and take its complex conjugate, and write it in the row way. This is the column way and this is the row way. And you just multiply pairwise, A1, A1 star, A1, A2 star, and A1, AN star, and so on. You just keep doing this, right? A2, A1 star, A2, A2 star. So we get a matrix like this. This operation is called an outer product. Okay. And what you do is that, so you have the state, which is specified by these n complex numbers. And by this operation, you have actually constructed a matrix. And this matrix captures the state of the system. And it is known, actually, has a technical definition. It's called the density matrix. Okay. So let me again recap the logic, because it's important to keep track of the logic. We had a notion of entropy. The notion of entropy required numbers, pi, but then we translated that we can take that notion and we can just have matrices, and from there we can compute entropy. And now matrices are naturally occurring in quantum mechanics. How do they occur in quantum mechanics? It occurs by by giving the state vector and taking it as taking this sort of object called outer product and computing rho. Okay. So this is your rho. Okay. Now let us do this. Let's do this complete operation for a particular simple system. It's called a spin 2 or a two-state system. Let's just completely do this operation. So here's psi A, B. Okay. So you can write it. So this is like A and B are two complex numbers. And you can write it in many ways. This is one way I think people in quantum mechanics know. You write it as A1, 0 plus B1, 0. And if you add this, you get AB. You can also write it A with an up, B with a down. Okay. Many ways you can write this. So this is your psi. Let's construct the matrix. So as I said, you have to do the outer product. So if you take this AB and put another one, A star, B star here, right? So it'll be AA star, then AB star, BA star, and BB star. And then how do you compute the entropy? Find its eigenvalues and sum lambda I log lambda I. So what are the eigenvalues? You can put it in some program, or you can just calculate. I think people who know a little bit BSc, I think they know how to calculate eigenvalues. I think even high school people do this. So the eigenvalues are something, is A squared plus B squared. It's 1 and 0. And if you compute the von Neumann entropy of this particular system, it's actually 0. So it doesn't seem very interesting. It's actually 0. If you compute it, it turns out to be 0. It's a very simple example, but it's an example what is called a pure state in quantum mechanics. And von Neumann entropy associated with that pure state is always vanishing. It always vanishes. It doesn't carry very much information. Now, so why am I talking about all this so much? Where is the information? Where is the interesting things, right? So the interesting things come when you think about something called the entanglement entropy. So here's the first word of the title. And if you have understood what is roughly entropy in this mathematical sense, and now we are going to define the entanglement entropy, which is much more interesting than the usual entropy, which for a quantum system, and in fact, for a pure state, it just vanishes, as a very simple example we have done. Okay. So let's generalize. Now let's go to this entanglement. So again, we start with this density matrix, or this matrix which we constructed out of this psi, or the wave function, and we break it up. We break it up into two parts. Okay. So separate these entries of this, of the system psi into two parts, A and B. Okay, let me explain that a little bit more. So, for instance, let's go back to this big psi, which I've written down here. So this big psi, you just break it up into first some parts, till something like A3 or some AK, and then the rest is the B. Okay, so you just break it up like that. So you separate the system into two parts. Okay, so that's the A and the B. And then you can, in fact, write the wave function in some particular basis. It's called a basis in terms of a sum of the A part, the B part, some coefficient, and vector in the A part and the B part. This is called a basis vector. You can break up the psi into the A part and the B part. And then, so here's an example, right? So initially I consider up and down, but now let us enhance it to two spins, up, 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 down, down, up, down, down. Now the density matrix, if you take this AB, this is an example of that system. If you take this AB and you take the outer product of psi and another psi, you will get this quantity, psi AB, CA star, AB star. And the elements of this are, some of them are in B and some of them are in A. You have to index it with B and A. The B is one part of the system and A is another part of the system. I'll give a more picture example soon. Some part is in B and some part is in A. And then what you're instructed to do is to construct another matrix called reduced density matrix, in which you sum over only the B. You sum over only the B. Now, once you sum only the B, you get another matrix in which only A's are present. Okay, so this summing over the B, that is one part of the system, is called, and we get the density matrix out of doing the sum, is called the reduced density matrix. And when you do that, you get something which only index A. I will do this for a very simple example. I think at least some people might understand the example. And then with this new matrix, you look at the entropy, row, log, row, trace, row, log, row. And so then you start getting interesting stuff. And the reason we will do this will be clear soon. Because first, when we did the usual notion of the matrix and constructed, we got 0. It was not very interesting. But when we separate the system into two parts and trace over one part, meaning sum over one part, and compute, look at the matrix and look at its entropy again, then you get interesting features. And that is what is known as entanglement entropy. So the entanglement entropy is, you have to, let me give that in words again, you partition the system into two parts. You somehow ignore the information of the B part, that is, by actually summing over all possibilities of the B part. Okay, and then you have only the A part, and and then you compute entropy using the von Neumann definition, and that is the entanglement entropy. Okay, so let me do this in this two-spin system, and here is your psi. So, and the green is this B part, okay, and the red is the A part. So it's some combination of the red part and the green part. And if you construct the outer product, meaning you take this and you take this this bra or whatever, this vector and its outer product, you get this matrix actually. You get this matrix. So it's a 4x4 matrix. And then you sum over the green part, right? And you get the reduced density matrix for the one part, for only the A part. And that is this matrix. Okay, this algebra might not be very quick for now, but this is sort of the illustration of what I have said. You get only the one part. And then, you compute, and it's in fact eigenvalues, cos squared and sine squared is the eigenvalues. And in fact, the entanglement entropy is this formula. So it looks very complicated, but this is the formula for the entanglement entropy of this particular state. So now it is non-trivial. It is not 0. Okay, it is some answer like this. But let's get some more intuition about this answer. If you look at it, when it becomes maximum for these values, okay, of cos theta and sin theta. Mind you, cos theta and sin theta is this combination, okay, and it becomes 2. And if you look at back, let's say it's cos squared and sin squared is half. So cos is, let's take the positive root, 1 by root 2. The state is actually 1 by root 2, up, down, down, up. So the state is entangled in the sense that you cannot separate out the first state compared to the rest. It's entangled, and it has entropy of log 2. Okay, it's quite high. But let's look at another example when theta is 0 or pi by 2. Then cos theta is like 1 for pi by 2 and so on. And if you calculate the entropy, it turns out to be 0. And if you look at cos theta, which is pi by 2, and this is this is 0 and this is 1, So, or the other way around, the state is like this, up and down. And here you can actually factorize, separate out the 1 and 2 very easily. It's a tensor product of two states, up and down, and it just sort of separates out. This state can be factorized, and its entropy is 0. Like a state which cannot be factorized, which is entangled, the entropy is maximum. So that's the sort of intuition you have to carry. Now, again, let me repeat. So we have this matrix. Somehow we divide it into 2 parts. And then when you trace over the 1 part and calculate its entropy, you get a quantity which is non-zero, which is called entanglement entropy. And it somehow, at least from this example, you see that it captures the notion that whether this A part is somehow entangled or mixed up with the B part. So here you see the entanglement entropy is like the maximum when you cannot really separate out this up, down, and it cannot be factorized. It's some linear combination. It cannot be just factorized. But here, when it's 0, it's just product of up and down. It's a tensor product state and it can be factorized. So this notion of entanglement entropy captures when the parts of subsystems are entangled with each other, or somehow cannot be separated out to each other. So let me again so this is sort of the first understanding of the entanglement entropy which you have, and and I've developed this definition from this very simple notion of von Neumann entropy and applied it to quantum mechanics. And to have interesting features for that von Neumann entropy in quantum mechanics, we needed to separate the systems. And this quantity which I constructed captures how one system is mixed up, one part of the system is mixed up with the other system. Okay, here now let us go a little bit more sophisticatedly and more complicatedly, and it's though we go a little bit more sophisticatedly, it is in pictures, so it's easier for you to understand. Usually we don't do people study quantum mechanics of course, but what nature, most of the theories of physics at the fundamental level are something called quantum field theories. And they're defined on, space-time and completely. Now, in that notion, how do you define what are these partitions? What are these partitions? Okay, because you said that we have to partition, one said that we have to partition the system. So the way one does that is like you look at a particular time slice of the system, and you look at a subregion like this A, and the B, the green part, is here. Okay, so the space splits into the A part and B part. It's just spatial separation. You take a time and look at a particular part of the space and remove the rest. Okay, trace out the rest, and then you ask the question whether this A is entangled with B. So of course you need the corresponding matrices to do all this, right? So given a particular theory, you need the corresponding matrices to do all that, and you can in fact do it, okay, for a certain class of theories. Now, if the theory is like a quantum wire or just one-dimensional system, then to partition the system would be just choosing an interval, right? It's just a wire, and you choose one particular section of the wire, which is L, or you can do 2 sections. So there are 2 intervals or 3 intervals and so on. The simplest one is 1 interval. So in this talk, for most of the rest of the talk, I will talk about just these one-dimensional systems, okay, which is just a wire, and we will choose only one section of it and remove the B part. The green part will be the rest, and the A part will be the first. Okay, so that's the sort of simple picture to have in mind all the time. The systems we will talk about are basically certain quantum systems. They live on the wire. Okay, they have, say, spins on the wire or so on, and then you are partitioning the system by just choosing a particular interval in that system. Okay. So now there are certain properties, like for instance, if you take the full system, if you take A to be the full system, it reduces to the usual notion of Boson entropy, in which there was no partition. Okay. And if it was pure, we saw that it was actually 0. And if the state is at finite temperature, as you know, if it is heated up, it gives you the thermal entropy. So as I said, these are generalizations of thermal entropy, and it should reduce to the thermal entropy under a certain condition, and that it does. Okay. Now, what is the application? So I said it's all very interesting. A lot of people are studying this and so on. So what are the various applications of this entanglement entropy? Now, I will just say many of the statements, but many of them might not be very familiar to you. But one of the things is that it is used to characterize degrees of freedom, and maybe I can explain this a little bit later on. This quantity, because I said initially, one of the statements I made was that this is very interesting now. A lot of people are studying it, and why are they studying it? Because basically, this new quantity in which you partition the system and you compute this trace log row, it has turned out to be very interesting because it serves as as a means to study various other properties. Now here is like the degrees of freedom of some particular system. 1 plus 1, the added 1 is the time, actually. Now this is the quantum wire with time, actually. This extra 1 is just the time. So, something called a Fermi surface, which I think people in Canvas matter know. It is good for studying that. It's good for studying quantum phase transitions and so on. And it's used to study, when a system becomes thermal, or when it becomes quite disordered. So it's used for that. Several applications, actually. And what I will be actually talking about is this application, which I've been looking at, and quite a lot of people also are looking at, is how it is playing a role in understanding something called holography and quantum gravity. Now then this holograph, now we come to the second word of the title. So I hope the first word is sort of clear, roughly clear. I mean, it's a matrix in which you partition it into two systems, and then somehow we remove one of the systems and compute one Neumann entropy or trace row log row. And now I have to tell you how that quantity is playing a role in holography or quantum gravity. Okay. It looks quite bizarre. That was something for quantum wires or some very simple systems, quantum systems, which you can visualize in a lab. But now we're talking about gravity and so on. Okay, so it's sort of a deep connection, and let's see how that connection becomes. And hopefully I can convey at least some aspects of that connection to you. Now, to go further, we need to know how these are computed. So I have given some very simple like matrix and so on where I've computed it, right? But how in general for these, say quantum wire or something, how it is computed? It's actually computed by means of an identity. It's hard to appreciate this identity if people don't know certain things in maths. But instead of computing trace of row log row, if you compute this quantity, where I take the row, which is the reduced density matrix, raise it to a power n, so you multiply the matrix n times, okay, and then take the trace, meaning sum the eigenvalues, sum the diagonal values, and take this particular thing, okay. And if you take the limit finally in the mathematical sense, n going to 1, you can prove that you get the entanglement entropy. You can prove it. So this is an alternate thing to compute. Basically, multiply the matrix n times, okay, and then do these operations. Okay. So it is in this way actually people compute it. You computed, evaluate the reduced density matrix, then multiply it n times, right? This multiplication of n times is actually done, in a sort of geometric manner, and that geometric manner is called the replica trick. So it's basically a procedure to multiply this matrix n times, okay? And when you do that for quantum field theories, or basically quantum wires, some systems which are seen in nature, you have to study that system in very complicated surfaces, okay? This is just to show how difficult it is to evaluate this quantity in theories which we like to evaluate, like quantum wires or something which you like to do. So the idea is that you have to take this matrix, multiply it n times, and that translates to studying the quantum field theory on a very complicated surface. Now, for instance, in this quantum wire, all right, which we always, and we choose an interval, choose a particular interval. Now, doing this rho a to the n, okay, translates to studying this quantum field theory in this complicated surface. So, so this is the line, and I've chosen this interval. This is the L, this is the line, and this direction is the time. This direction is the time. So I've chosen this interval. Now, so therefore, this the theory, this quantum wire is this wire along with time. This is the wire along with time. So you have to study the theory multiple times. That's why it's called replica. And somehow this surface is connected to this surface by this pink sheet. So it's quite a complicated object to study. And you have to study this, the theory on this particular surface to evaluate this object, this thing called the entanglement entropy. So it's quite involved, I mean, setting up this whole calculation, and very few exact results are known actually to do this. Okay. So there are other techniques, but evaluation of this quantity, though it's very interesting, people studied it and so on in some conceptual way, but explicit computation of that is quite hard, and very few systems, I think, studied exactly. Okay. And experimentally, just to people who are interested experimentally, this has not been observed. Only the n equals 2 case has been studied in this paper. I don't know the current status. Maybe they have improved actually. So maybe n equals 2, meaning, as I said, what is n equals 2? It's this particular, this closely related quantity called Rene entropy, where you take the reduced density matrix, multiply it to n and compute this. For n equals 2, that has been computed. But what we need is to compute it as a function of n and take the limit n equals 1 for the entanglement. So you can imagine how difficult it is. So, so that is the experimental status, at least for some time, I know. And now I'll go to this topic in which how it is connected to holography. I have to, of course, define what is holography. And then we will somehow relate the title. Okay, so we roughly know what's the meaning of entanglement entropy. And now we will sort of relate it to the title, the complete aspects of the title. So again, we will go to our favorite system, the quantum wire. And there is a system called the free boson, in which, as I said, there is some notion of, it's called a conformal field theory. These are like quantum wires, but they are at something called a critical point, meaning they have no scales in this system. They are called conformal field theories. Actually, there is no scale in that system. There's no mass. There's only, I mean, this happens for very low energies, such we can approximate things like that. In fact, graphene is an example of such system at very low energies. So, so at very low energies, these things have no other scale. The mass doesn't kick in still, and we can call it, and it's also called a theory at the critical point. So we can this is one particular example, a free boson. So what I'm trying to do is give you examples of the results, very simple results which are known. So if you take the quantum wire, which is we call a conformal field theory of a particular kind, and evaluate it, partition it into these parts and choose this interval, you get this particular answer. It's a very simple answer. It's actually an answer for any theory without any scale in 1 + 1. There is a number in front, and that number is called the central charge. Other than that, everything else is this particular logarithmic growth. With delta is the same as L, actually. I drew it like differently. This L is the same as delta. So it's a function of L. It's logarithmically dependent on L. And there's a sort of coefficient in front of it, which is called the central charge. And that central charge changes for different theories, but that is for one particular quantum wire, it will be one kind, and another quantum wire will be another kind, and so on. Now we can actually take the quantum wire and make it a circle, for instance. That's the conformal field theory on a circle. And if we calculate it, the formula changes slightly. The periodicity of the circle comes in, and the sine function comes in here. So that's another sort of exact answer, which is known. This is the interval of our choice. Now, if you take the theory on a real line, but you heat it up at some temperature, and you compute, and again partition the system into this subsystem L, and this L of length delta. And so it actually becomes this particular formula. Again, the same formula, C/3, that formula is there, but this becomes, instead of sine, it becomes sine hyperbolic. It's a very nice pattern. It becomes this particular formula. Okay. Now, for the Rene entropy also, there is this formula, general formulas like these. You see, when n = 1, it becomes C/3. So, this for a single interval, for a one-dimensional conformal field theory or a system without any scale, you don't have any other information other than the central charge. I mean, you can figure out whether it's heated or whether it's on a circle by the dependence inside the log. But other than that, you have only this number C, which is a notion of degrees of freedom or the central charge. And in fact, there is a formula like the Stefan's formula, which people learn in physics, even in one dimension. And it's not very different from there. The Stefan's formula in this particular case will be C by beta C. It goes linearly in temperature, while in 4 dimensions it goes with a different power, but here it goes with T. And other than that, coefficient appears, that same coefficient appears here. So other than that, there's not particularly great information of this entanglement entropy. Okay. But what, for these simple systems, what happens is that when you make the connection with holography, it becomes very interesting. So let's do that, and then you will get an idea, the notion of the holography. So this is universal in the sense that the formula is so simple, and it just depends on one number. That's what here it means. And somehow it must be, there is a notion of holography which is already known in the literature. And since it's so simple and nice and it's universal, we should be able to see this in holography. And how do we see this entanglement entropy in holography? Now, I have not defined holography, and I will define it soon. But what you have to take away is that, this computation of entanglement entropy took a lot of effort. It in fact, one had to compute this matrix. You had to do a lot of stuff with it and get a number at the end of it, right? That was the entanglement entropy. Okay, but in this holographic prescription or holographic notion of computing this, it actually becomes very geometric. Okay, not this algebraic calculation of finding this replica surface and doing things with it and so on. So and this was found actually in 2006 by these authors. And let me explain that using also, and while doing that, I will explain the notion of holography. Okay, so holography is a duality, or duality means something is two things are the same. So dual means there are two things, and somehow two things are the same, which relates quantum field theories or many body systems. Okay, in say d+1, this one is time and this is the spatial. So if it was a quantum wire, this little d was 1. Okay, two theories in gravity. Okay, so it looks quite amazing, right? Because you have quantum field theory, which is there's no gravity, there's just a many body system, and that is related to theories in gravity. Okay, and how does that happen? I mean, and the theory in gravity doesn't stay in this dimension; it stays in one higher dimension. So this green is the extra 1 dimensions. Okay, so it's a duality, meaning two things are related. One is the gravity theory, and one is this, many body theory. And the gravity theory is in one higher dimensions, and somehow they're related. And like all known dualities in physics, I think many people might have not come across the notion of duality in physics. It's something strong, weak. And in this case, it relates this one-dimensional quantum wire, this is the time, to a theory of gravity in 2 dimensions, or 2, and this is time. So let me give you a picture. That's the easiest. Now, this is a cylinder. The quantum wire you can think, or the quantum system, or the many-body system, is this wire. Okay, this round wire. I mean, it's basically a string which is right here. That's the wire, right? And that's on the boundary. That's the edge of the cylinder, and the time runs upward. So this is the time. So the edge of the cylinder and the time. Now the gravity. So that's the boundary, as they call it. The gravity is inside. Gravity is inside, actually. So therefore, if you combine this added radial direction along with the angular direction and time, it becomes a higher dimension. So this extra radial direction is the extra direction, and the gravity lives here, and the quantum field theory or the quantum system is just here, right? So now we were computing the entanglement entropy on this quantum system, just on this system. But how are we going to use notions of gravity to compute this entanglement entropy. Okay, that seems, I mean, the duality itself is quite mysterious, and there are many checks and so on. I can't go through all that. It has been studied for about 25 years, but it is mysterious. But let me tell you, at least for this particular quantity which we studied. So the study, what we did was we partitioned the quantum wire into an interval, and there was something associated, entanglement entropy associated with that interval, and it was a formula like C by 3, some number C by 3 log of because it was periodic, it was sine of that interval, a sine function of the interval, or something which is proportional to the interval size. Okay, so that was the formula, okay, which we got by computing it in field theory. Somebody computed it for you. Now, how do you compute the same quantity in gravity? Now, so as I said, this gravity, okay, now it's sort of, people might think it's a little complicated, but gravity is a theory which has a metric or a way of defining distances. Okay, so there's some notion of defining distances. This is a way of measuring distances. And how do you evaluate this entanglement entropy in this particular theory, in this particular, using the extra dimensions, basically. Okay, so what we have to do is basically, here it is. So here is where the wire was. Okay, and we chose this A, this interval A. We had to trace out the B. Now, in this gravity, there is a space inside. Okay, and what you are supposed to do is consider the shortest path from A to B. Okay, so from the end point of the interval, the shortest path. Okay, it's very geometric. So you take the shortest path, and in this particular theory of the gravity, the shortest path doesn't go here. It doesn't go here. It just goes into the space. So you take the shortest path, okay, and find the length of the shortest path. Okay, that is what I've written here. So this is, you take the shortest. So you look at a constant time slice. What I mean is choose a particular time. Okay, choose the endpoints of the interval on the wire where you are interested in the entanglement entropy. Choose the shortest path. Okay, that's what I've written in formulas here, which people, okay, I can explain if people are interested, but this is the thing in pictures. So it should choose the shortest path and find, that is called the geodesic. The shortest path is called the geodesic between the endpoints, which is P and Q, and find the length, okay, and divide it by the Newton's constant. Okay, that's where the gravity comes. And this formula was actually inspired by Hawking-Bekenstein formula. But it's a formula from that translated into this three-dimensional gravity. But this prescription is very simple. In fact, it's very geometric. Here is the wire. Again, I repeat, find the shortest path between that and just evaluate its length. And you take the length and you divide it by this Newton's constant, 4 times the Newton's constant. Now, here's a calculation of that. Actually, I've done this calculation for this particular case. And lo and behold, if you calculate this length, and there is a connection between the Newton's constant and the central charge, which was discovered earlier, actually, of the theory. And if you use that connection, you get the same expression, which you computed in a very complicated way. You get the log. There was an epsilon, that was this notion played by this, but the log, that sine pi delta by L, that same expression comes out. And here the calculation is very geometric. Again, just to see the picture, it's very geometric. The calculation is just, you take that system, which was the quantum wire on a circle, and then, you just evaluate the length between, which is inside a space, gravitational space. So that turns out the entanglement entropy. And here you see the power of this holographic descriptions. So when I say holographic, it's like, so let's give that a little bit more sort of in a picture way. So the hologram is the object which is here, which is like one-dimensional lower, and this is the theory, the bulk theory, and the hologram lives here. That's why they call it a holography. That's sort of the meaning of it, why they use that word. So this quantity becomes very geometric when you think in terms of gravity. So that you see, the entanglement entropy has become sort of very interesting. It basically is length in gravity. In some sense, it's the shortest length in gravity. So this interest actually comes, our interest actually comes because of this geometric connection actually. And it might, I mean, when I explain all this to you, it might seem very, tenuous. The connection might not be, oh, well, it's very sort of, is it really connected or not? But actually, like, people have studied this very in detail, and studying it in much more detail helps us to understand not just aspects of gravity, because the gravity is connected to the quantum theory, and it also helps us to understand the gravity. So that's the sort of focus of most of the people's research in this area. They try to understand gravity better, as well as they try to understand the quantum theory better. Okay. So in fact, now maybe I can sort of both the topics are connected now. You understand what's, roughly speaking, entanglement. Do I have time? How much time do I have? 10 minutes or something?
So, yeah, it's up to you, sir. 5 to 10 minutes you can take.
Yeah. Okay.
Yeah.
So, so you sort of have the quantum system, and then you have a notion of, you understand what is entanglement entropy, and you understood what is holography. At least qualitatively, you sort of have that notion. And but how can you get more information? Okay. So the formula which I showed you was very simple. It just had the central charge, the C by 3 and some logarithmic dependence. But there are more complicated situations in which you can get more information. And the information should have more detailed properties of the conformal field theory or the quantum system, not just the central charge, but it should also be universal, at least for a class of theories. And that will enable to check these geometrical proposals. And this is the strategy which many people adopt in their research. Look for corrections to the single interval entanglement entropy or any entropy. Evaluate them precisely in the conformal field theory. This would involve evaluating it on those replica sheets and so on. It's a complicated process. You evaluate it and then show that it's universal in some sense, and then you use geometry to test whether, have you done it correctly, or the geometry, should we correct something in the geometrical dictionary, and so on. So this is sort of some activity which a lot of people do. Okay, and it improves both holographically and the notion of the quantum system, and that is the strategy which we study actually. And so let's see. So here's one sort of example. I will end it. One sort of little thing which we found, so that you get a notion about the kind of research which people are doing into this. Okay, I've told you this connection, entanglement entropy, and holography. That is sort of the thing you have to take back. At least this very geometric prescription of computing the entanglement entropy as a length in gravity is what you have to take back. But here is something which we have been looking at, and just to give you a flavor of the research. Okay, so just connected to the single interval itself. So it's called a time dependence in quantum quenches. Now, so we are considering excitations. So on the conformal field theory. So last time we didn't, on the quantum system, we did not excite this quantum system. We either held it at finite temperature or we held it at vacuum. So here we hold it at finite temperature, and we excite it. We put a pulse. Okay, so here's a picture. I think the picture is better. So this is the pulse. This is the pulse. And here is the entangling interval, that A system, L1 and L2 is here. We start the pulse, okay? And the pulse moves on the light cone because there is no mass. So it'll move, as I said, these theories don't have mass scales. So they'll move on a light cone. And the pulse moves on the cone. Once it hits t is equal to L1 at the speed of light, it moves at the speed of light at the light cone. Once it hits the first interval, the entanglement entropy will jump. Okay, because the pulse, some quantum thing has come inside, it will jump. Now, in the real system, this blue thing is sort of the jump. You see this blue chart, that's the jump. Now, people actually speculated that it jumps like this with a square well jump. Now, what we have done is basically found corrections to the square well. This is one of the things, one simple work with a student, is that we have found corrections to the square well jump. They said it jumps like this square, but there is this correction. In fact, it has this horns like, and this red correction is something which we found. So here you see, this is the usual entanglement entropy, as I said, at finite temperature, that C by 3, and then the sine hyperbolic. There's a jump. And the jump, people said it was just a square jump like this. They said it was this red part. That's by these authors. They said this, it was the square part. But we found that there are these corrections. Okay, the corrections are of these kinds. They actually, the real one, in one case we could do it exactly, and that's the blue. But in a generic system, the corrections are of this kind: sharp rise and then sharp fall like this. This sharp rise and sharp fall we could capture, and that's this formula. This sharp rise and sharp fall is a formula which we sort of found. Okay. And that also is quite universal. And what is interesting about this sharp rise and sharp fall is that we actually could do the same calculation in gravity. Okay, and there it's it's quite complicated. When the system is at finite temperature, it actually, there's a black hole inside that cylinder which I talked about. There's a black hole, and this pulse is actually a particle falling into the black hole. So you see the interesting thing of this holography, entanglement entropy. Here it is just a pulse moving into this interval. But when you think in terms of the gravity, it becomes a particle falling into the black hole. Okay, so and we could do this calculation in gravity and actually verify that this correction is reproduced in gravity as well. So that was one of the things we did. And maybe, yeah, there are various other things, but yeah, it's just to give a flavor of something. So let me just conclude. So as hopefully I've convinced you, entanglement entropy is a reasonably interesting quantity to study in quantum field theories. And it has been a driving factor to obtain these universal results in these theories. And it's useful in holography because in holography, this quantity becomes very geometric. And you see even in this pulse business, it becomes very geometric. It's a particle falling into a black hole. And there are many things one wants to study about that. So, so this entanglement entropy captures certain aspects of it. And studying this, there is more, we understand there are more refinements to this simple geometric proposal, and there are more lessons to be learned. So I will sort of end at that, I think. Yeah. Hello? Yeah.
Yeah, sir. Thank you, sir. Thank you, sir, for such an informative and knowledgeable talk. And we look forward to have such interactive sessions with you again. And before we'll proceed further for the formal vote of thanks, I would, sir, can we take some questions?
Yes, yeah, please.
Yeah. For this, I would like to invite one of our student coordinator, Anshum, to take this forward. Over to you, Anshum.
Yes, thank you, ma'am.
Thank you.
So now we are open to a short question answer session. You can type your questions in the chat box.
How do I see?
We already have some questions. Sir, I'll just read it out.
Okay.
So the first question is, how can we check a particular state is entangled or not?
Yes, as I said, I gave you a very simple example, in which there was a 2-bit system, right? And when the system was entangled, the entanglement entropy was non-zero. When it was not entangled, where you could factorize, it was 0. So it's basically 0 versus non-zero. I mean, if you compute this quantity, if it is 0, the system is not entangled. And if it is non-zero, it's entangled actually. Yeah, it's very simple diagnostics when a system is entangled or not. But you will have to partition the system correctly, meaning in the sense that you have to find the correct, okay, you want to find this is part of the system is entangled to another part of the system. So you partition it correctly, and then you have to do this computation of trace, rho, log, rho. That computation is pretty hard actually, but once you do that, and if it is 0, it's not entangled. If it is non-zero, it's entangled. Yeah. Go ahead, another question.
Yes, sir. So the next question is how density matrix is different from Gibbs and entropy.
Gibbs entropy is, it's connected to thermodynamic entropy. It can be related, but this density matrix is set up for actually, and the Gibbs one is very classical actually. It's just in usual thermodynamic system. This entropy, density matrix is set up for actually quantum systems. As I said, in quantum theory, matrix are more common. So we needed to define notions, of entropy for a matrix itself, right? Because you didn't have temperature even, it was just a quantum system at 0 temperature, just usual quantum system, and we needed to have a notion of entropy even just for that. So that's why one generalized the notion of entropy to a matrix. Okay, so because in quantum theory there are matrices. So the Gibbs is for very classical systems, and it's more connected with pi log pi definition than this using a matrix actually. So you can use this entropy, and you can actually in some limits, of course, it goes to the Gibbs, but this is a much more general concept actually. Yeah.
So you also talked about quantum gravity. So there's a question: does it mean correlation of entangled entropy with gravitational space-time?
No, I meant very simple. This is a more complicated notion. I actually meant very simple. Let me again picture that picture. Actually, if we take home, it's a good thing. If I sort of people remember that picture, I think I'm happy. So here it is. So you see, the quantum system is a one-dimensional system, which is this ring. Okay, and we are choosing a subinterval. That's our partition. This A and this rest B. Okay. Now we want to evaluate the entanglement entropy of the system A, of this partition A. So we know by calculation it is some C/3 log something. But in the gravitational system, you're told to do something else. You're actually told to compute this. All you do is measure the minimal length from this endpoint to the other endpoint, but in the gravitational theory. Okay, so you measure that minimal length and just divide by the Newton's constant, right? And then you get the same result, exactly the same result as what you would get for the field theory or for the quantum system. And that is what is amazing about it. It's a completely different way of calculating it, and you get the same result. So that's what is the holographic description. Because when I say holography, I've divided, two things are the same. And these are the two things. The formula which we evaluated using this multi-sheet stuff and everything, which was C/3 log something. Here you just evaluate it from the length. If people sort of take that home, it's good actually. Yeah. Okay. Any other questions?
Yes, sir. So I have a question actually about quantum mechanics in general. I'm keenly interested in the subject.
Okay.
So there's a concept. There's a notion that the concept of time is connected to entropy.
Right.
So how is that connected to entropy? How does entropy guide the arrow of time?
Well, yeah, it's sort of, it's heuristic notion. It is not as precise. It's basically because, entropy always increases, right? That you can show that entropy always increases. It's part of the, not show, it's part of the,
So it's the second law.
Second law. Yeah, second law. And therefore, the time always flows in one direction. So I think that it's that notion that entropy increases. And so therefore you can associate the increase of entropy to the increase in time. I think, that is the arrow of time, which because entropy flows in one particular direction, it always increases, and that's the direction time flows. I think that is the notion which people use. This is thermodynamic entropy, by the way.
So does that restrict time travel?
Well, I don't know. Time travel. Yeah, of course, you cannot decrease entropy, but time travel is restricted not just with this. It's just restricted using the fact that light travels in light cones. It travels with and just with that itself, it's restricted. Actually, you don't need temperature even to have that notion. You don't need temperature. You don't need the notion of temperature to say that time is causal and our systems are causal. You don't need the notion of temperature even. It's more microscopic, the fact that things are causal. Actually, Okay.
So there is another question.
Okay.
What is your favorite interpretation of quantum mechanics?
I don't know. I use very pragmatic notion. I have not thought very much about the interpretation of quantum mechanics actually, but I guess the usual. The Born interpretation. Many worlds I don't know very much, but the usual pragmatic notion. of quantum mechanics, I think, is what I mean, we are very practicing physicists, right? So we don't, I mean, I think as far as I know, I've not thought very deeply about the meaning of measurement in quantum mechanics. There are some physicists who do that, but I have not thought about that actually to sort of answer that question in a very convincing way. So essentially the way we use quantum mechanics, because, you know, as Professor Ravi said, I have to convey some notion, I mean, some flavor of the research. So the way we use quantum mechanics is just pragmatic. I mean, so the equations are given, right? And you know, we use the same those equations. We have not thought about the interpretation of the measurements. I mean, at least for these things, we don't think very much about the interpretation of the measurement problem and so on. Okay, so there is this density matrix. How does it evolve? I mean, these are the questions we ask, and that equations we try to find out from the very first principles of quantum mechanics. Yeah.
So, and one last question. So, entanglement is the notion that information can travel faster than the speed of light. So, does that? How does that the theory of everything? I mean,
is it? I mean,
does that restrict the theory of everything or of some sort?
I don't think so. I mean, I don't know whether it travels faster than, I mean, speed of light. I mean, like it is that, you know, when a system is entangled, that object can be transported far. I mean, like if for instance, this, well, if I have to go back, there was one system in which I wrote down it was maximally entangled state, which is up, down, and down, up, right? Yeah, here, up, down, and down, up. For instance, this system, like if you separate these two things very far away, if this wave function can be separated in such a way, but you know that these two cats are still entangled. So measuring one particular cat, you know the other one, though it is very far away. I mean, I think maybe that is the notion, I think, of...
Yes, sir. Einstein also said, "No spooky action at a distance." About entanglement.
Right. Yeah. I mean, I think, yeah, he thought about it, but not maybe so quantitatively. My impression is, yeah, I think, yeah. Yeah, he thought about it. But, you know, when you, as advice to students, but when you think about all these things and when you read about them, I think you have to quantify them. I mean, everything has, you have to quantify them. Only then I think you can take it far. I mean, just a general advice. I mean, you have to quantify them, and then you can take it far, actually. So here, as I said, when you said something about notion of entanglement distance, I brought to this equation. I brought you to this equation and tried to show you exactly something, at least an equation, and showed you what it means to say something like that. So you can, most of us think in qualitative ways, but when you actually do research and when you want to present your results, you actually have to do it very quantitatively, actually. Otherwise, people don't accept the results, actually. So that notion you have to sort of take, actually. At least one flavor I want to convey is that particular flavor, actually. Yeah.
So you mean let the mathematics guide you?
No, not exactly mathematics. Of course, physics intuition guides you, but you have to make it very precise and rigorous, I think. It can't be just words and so on, right? I mean, nobody will, I mean, take you seriously. It has to be reproducible. Yes. It has to be reproducible, meaning even if it is an experiment or even theory, that equation, somebody else has to work out that equations also, right? Somebody else has to reproduce that equations. Only then it's acceptable, those things, actually. Yeah, that notion you have to take. It is not just things from the popular book. I mean, of course, that is good for getting motivated and getting into the subject. But as I said, in terms of research, you have to take it really a little bit ahead. And that requires preparation. It requires sort of training in a particular very narrow way for a long time. And, yeah, if some people are motivated, it's good, actually. Yeah. Okay. Yeah.
All right, got it. Thank you, sir.
Okay. Any other question? That's okay.
Dr. Asu, you unmute yourself.
Thank you. Sorry, sir. Thank you. Thank you, sir. You were very right. Research requires it's a way of the hard work, and a lot of devotion is required for that. And not only the books, but many things is there to get a valuable research continue. Yeah, very true, sir.
You need to get good mentors also.
Yeah,
Mentors are
definitely,
going
sir. Without that, it's not possible. I know. Thank you so much, sir. Now I would like to invite Dr. Radhika Gupta to give formal vote of thanks. Thank you. Over to you, Radhika.
Yes, thank you, ma'am. Thank you, Anshum. Thank you, ma'am. A very good evening to our esteemed speaker, Professor Justin David, our principal, sir, Professor Rabi Narayan Kar, the IQAC coordinator, Dr. Kusha Tiwari, all the respected teachers, the lovely audience, and to all my dear students. I'm Dr. Radhika Gupta, Assistant Professor, Department of Chemistry, Shamlal College. It's a great honor to propose a vote of thanks on this very first lecture of SLC Eminent Lecture Series 2021-2022 on the topic Entanglement Entropy and Holography. The SLC Eminence Lecture Series is being launched with the purpose of offering a holistic academic approach to the young pupil by fostering innovative thinking and research aptitude through interaction with eminent speakers and professionals from varied areas of science and technology. We believe that such an engagement of educators and students with the experts would enable them in harnessing their skills and creativity to accelerate the innovation at personal as well as organizational levels. At the very start, I'm deeply thankful to Professor Justin David for accepting the invitation and for being so generous to deliver such an informative talk in a way starting from the grassroots levels of quantum mechanics to entanglement entropy and holography involving basic mathematics, which could be the best possible way for the undergraduate students to understand. Sir, we thoroughly enjoyed your talk. It was indeed very useful at the same time, as the talk introduces many new terms to some of the students who are still in their preparatory phase of higher science. But because we had a diversified audience, including people from various backgrounds, such as mathematics, physics, and also chemists, I'm quite certain that our audience have been benefited. I'm also sure that the students have extracted some new information from your lecture according to their interest and expertise. And with this, yes, sir. And with this, I think the real purpose of organizing this lecture series and motivating students to come out of their comfort zone to learn new things is going to be fulfilled. Sir, I thank you for making time in your busy schedule to speak at this event. Thank you again.
Thanks for having me. Yes.
Thank you, sir. Now I extend my sincere thanks to our principal, Professor Rabi Narayan Kar, for providing perpetual encouragement, guidance, and support throughout the event. Ever since I joined the college, I have seen him engaging in every activity, regardless of the level on which it is being organized. So thank you, sir, for providing us the opportunity and for being with us. Your leadership and positive attitude has helped pull us through. I also thank Dr. Professor Kusha Tiwari, Coordinator IQAC, for her constant support. Special thanks to Dr. Ashu Gupta, Overall Coordinator DBT, Department of Chemistry, and Dr. Monica Goyal, Professor Physics Coordinator, DBT, for their eternal presence, support, mentorship, and guidance at every step. I also like to appreciate the sincere efforts of all the student coordinators, including Aviral, Vansh, Anshum, and Ayushi, for the systematic planning and execution of the event. You people have really done a wonderful job. Thank you, everyone. Besides, I thank the office staff members, including Mr. Suman, Mr. Gaurav, and Mr. Tarun, for providing all the technical help and making this event a great success. Last, but the most significant words of thanks must be given to all the participants, including students from various streams and teachers, for their patient listening and for being a splendid audience. I hope you all have enjoyed this event and gained valuable insights. Thank you, everyone. Hope to see you all again in all our future events. Now I request Anshum to make some announcement, I think.
Yes, thank you, Radhika, also.
Thank you, sir.
For not leaving even a single person's name in the list.
Yes, I think must deserve the name to be appreciated.
Okay.
Yes, Anshum,
Yes,
please.
Anshu.
Now I would request everyone to please turn on their cameras for a picture.
Please switch on your video so that we can have a photo. I request everyone to switch on your videos, please.
Acha, we have some also distinguished audience here, so I could just make out. Namaskar, Professor Pradyumnaji. I could just see his face. I could make out Professor Pradyumnaji.
Pradyuman Kumar sir is there. Yes.
Welcome.
Please switch on so that we can have a. Please be fast. All of you, I request everyone. Anshum, please take it. And when you have taken it, please inform Radhika ma'am.
Okay, ma'am. Yes, ma'am, I've taken it.
Done? Thank you. Thank you so much.
Thank you, Professor Justin. It was a pleasure on our part to have you with us. And again, I would request you to have a mentoring session for the young faculties also, as we have been discussing.
Okay. Okay. Yeah.
So
Thank you.
Thank you.
Thanks, sir.
We're looking forward to have another interactive session with you, sir. Thank you. Thank you so much.
Thank you. Thank you. Bye.
Now we can, I suppose we can leave the meeting.
Yes, ma'am. Thank you, everyone.
Thank you, sir. Thank you.
Madam, end the meeting.
Please.
Okay, ma'am.